Ionization energy. Ionization energy. All right, ionization energy, the trend is actually similar to that for electronegativity. If you remember the other day, we talked about electronegativity, and it was about who wanted electrons the most, okay? Ionization energy has to do with who is it hardest or easiest to steal electrons from. Okay. Who is it the hardest or the easiest to steal an electron from? So basically, the actual definition, so that's what it means. The actual definition is the energy required, to steal an electron from an atom. Okay. I'll give you a second, let you get that down. All right, again, when you're doing a trend, I need to know, does it increase or does it decrease? And one is the trend for the period or the row. So I need to know that for a period or a row. And then I also need to know what the trend is for a group or a family. Okay. So thinking about what we talked about on Monday as it relates to who wants electrons the most, okay, and how many electrons atoms want, okay, and all that stuff. Think about who would it be the hardest to steal from? Who would it be the hardest to steal from? Okay. Any ideas which family or which direction the hardest to steal from? Exactly. So Ariane said the hardest people to be steal from are going to be the noble gases, and he's absolutely right. Okay. The noble gases, remember, they have 8 valence electrons. Okay. They don't want to give up electrons at all. They don't want to gain any, but they don't want to give any up either. Okay. They're going to be the hardest to steal from. Okay. So now what about this family over here, the alkali? They're the easiest from to steal from. Hey, can I have your valence electron? Absolutely, take it. They don't even want it, okay? So if you're thinking about within a period, the trend should be kind of easy. It should be, it increases going which way? The energy it takes to steal from them. Because remember, it's going to take a lot of energy to steal from groups that don't want to give them up. So it should increase going which way? Left or right? Going to the right, okay? So as you go this way, it's going to be an increase in energy that it takes to steal an electron from. Okay, so for the group trend for the period or the row for ionization energy is going to increase as we go to the right. Okay, that makes sense. The noble gases, they don't want to give up anything. Okay. Remember these first 3 groups, group 1, group 2, and group 13, they're giving electrons away. They don't even want them. Okay, so like this group, they're giving electrons away. You don't need any energy to steal from them. I don't want them. You can take them. Okay, but then your other groups over here, these guys, they're like, look, I already have 5 electrons. I'm trying to get 3 more. These have 6, they're trying to get 2 more, and these have 7. They're just trying to get 1 more. They're definitely not giving any up, okay? So as you go to the right, ionization energy, or the energy required to steal an electron is going to increase as you go to the right. Okay. All right. So that's usually the easier one. And if you notice, let's think back to what we realized the other day. Remember, electronegativity is who wants electrons the most. It also increased towards the right. So it makes sense if electronegativity, let me do this. Sorry. If electronegativity increased as we went to the right as well, why is this changing? Sorry. Increases. I love this book. Look at me writing and nothing's happening. Don't you just love technology? I just love it. All right, let's try this one more time. Electronegativity, okay, would increase as you go to the right as well. That should make sense because electronegativity was asking who wants electrons the most. Ionization energy is saying who is it the hardest to steal from. So they should be the same because it should be harder to steal from the people who want it the most. Okay, so the trend is the same for electronegativity and ionization energy. All right, so now let's think about within a family though. Okay, let's think about within a family. Usually going within a family is the harder ones for these. Okay, all right, I want you to think about, I'm going to do some board diagrams again. Okay, I'm going to do actually I already have a picture, so I'm going to do this fluorine, chlorine, and iodine. And I think I already have a picture. Give me a second, because it was a lot of dots to draw and a lot of rings. So give me 1 second. Let me see if I can pull it up. All right, so here we go. So I drew board diagrams of fluorine, chlorine, and iodine. Okay. Now, we're trying to figure out who is it easiest or hardest, however you want to think about it, to steal from, okay, to steal an electron from. Now, I want you to think about this in terms of, let's just say for right now, let's think about it in terms of money, okay? So let's say the electrons are single dollar bills, okay? They're single dollar bills. All right, so fluorine has 9 $1 bills. So he has $9. They're all in ones, okay? And then chlorine has $17. Again, all in ones, okay? And then iodine down here has $53, and they're all in ones, okay? All in ones. Now, let's say these are all your friends, okay? I don't want to encourage stealing. Let's say they're all your friends and you need to borrow $1. Okay, you need to borrow $1. Who is either most likely to say, yeah, sure, you can have $1, which would mean it would take less energy to get one from them, or who is going to be like, I don't know, I'm not going to be able to give you one. Okay. Yes, but out of these three, out of fluorine, chlorine, and iodine, and this is how much money they have, those are their electrons. Who for what? For least likely or most likely to give you $1?
Least likely to give you $1.
Yes, fluorine's gonna be, look, fluorine's got $9. He's like, look, I just got $9. If you're gonna go steal $1 or borrow $1 from someone, go borrow from iodine. He's got 53 of them, right? So the hardest to steal $1 from, or the hardest to borrow $1 from, is going to be fluorine, because he only has 9 measly dollars. Okay. So in the case of this, who is the hardest to steal from, or how would ionization energy increase, which means it's hard to steal from? This one would increase. Remember, these are all in the same family. So I think that was Was that you, Brooklyn, that said that? I think that was Brooklyn. That said fluorine would be the hardest to steal from, okay? So it's gonna take the most energy to steal from fluorine. Does that make sense? Because if it doesn't, let me know. What do you guys think? Does it make sense that if Charlie had $53, Mandy had 17, and Melissa had $9, Melissa would be like, go borrow $1 from Charlie. Because I only got 9. I only got $9. Go borrow from somebody who has more money than me. Okay. So this is going to take, you're going to have to put in your most effort, most energy, most convincing to try to get this one to give you $1. Okay. So for ionization energy within a family, would it increase going up or going down? Look at where fluorine is. Increase would mean that it gets harder to steal from. So increase going up or going down?
Down.
Now going down would mean it would be harder to steal from iodine. Who's the hardest to steal from? Yes. So now if you guys want me to say it the other way, you could also say, if you don't like saying increase going up, you could say decrease going down. Okay, you can say it the other way. In other words, it gets easier to steal as you go down. It's easier to steal from this guy than it is from this guy. So you can say decrease going down if you want. Okay, if that makes more sense. All right, whatever makes more sense to you. Because I mean, if it increases going up, then it's going to decrease going down. Okay. All right, does that kind of hopefully make sense? Okay. All right, so let's try some practice problems. Okay, let's try some practice problems. Let me erase this. Okay. All right, let's say you had, I wonder if I can just do a little question mark. Let's say you had vanadium, okay, and let me do a star actually. Well, vanadium and nickel and calcium, okay. Can you guys see those? Let me do boxes. That'll be easier for circles. All right, so I said vanadium, calcium, and nickel. All right, so my question is, who would it be, who would have the, let's say the highest ionization energy? In other words, who would it be the hardest to steal stuff from? So take a second, think about it. Who would it be the hardest to steal electrons from? Would it be calcium, vanadium, or nickel? Think about it for a second. Okay, any guesses? Anybody online? What do you guys think?
Maybe calcium.
Okay, and if it's calcium, tell me why.
Because it increases from left to right and it gets bigger numbers. So like the least number would be hardest to steal from.
Okay, so listen to what you said, because you gave the right reasoning. You said it increases from left to right, and it would be hardest to steal from as you go this way. But you told me calcium. But you said it increases from left to right. So you gave me the right reasoning, but you said the wrong answer.
But wouldn't it be like, isn't it like the smallest number is like the one that you can't steal from, like it's the hardest to steal from. So wouldn't, like, why is it not calcium? Because isn't calcium the smallest since it increases when it gets to nickel?
I see what you're saying. So you got to think about it like this, though. If they are in the same row, okay. So this is the thing that can throw us off sometimes. First thing you should ask yourself is, are they in the same row or are they in the same column? All right. Now, if they were in the same column, then yes, we should be looking at it like this. Because see, these guys were all in the same column. Okay. So, but these are in the same row. So let's think about this, Mandy. Remember, everybody wants to look like who? And this is a good question. I'm glad you brought this up. Who does everybody want to look like? What family?
The noble gases.
Noble gases, right? So everybody's trying to move to look like these guys, okay? So who's the closest to looking like this guy, this family?
Nickel.
Nickel, right? So if he's the closest to looking like these guys, he's not going to give up anything. This guy is the least likely to look like him. He's going to give away electrons. Remember the video we watched the other day said if you had less than 4 valence electrons, you're not even trying to get them, you're trying to give them away. So this guy is trying to give them away. And they probably all are, but this guy is really, he's like, I just got 2, I just need to get rid of them, okay? So he is trying to give them away more. This guy is closer to looking like the noble gases. So he's gonna be an increase. Now, so the answer for this, and I did have people in the chat tell me too, the answer is nickel, and it's in here in class, so you guys were right. So the answer for this one is nickel. Now, Mandy, take that same logic that you just had about who has more, and let's say I said, what about, let's say carbon, germanium, and lead, okay? Who has the most, so this time I want to know, who would it be the easiest to steal from, or who has the lowest ionization energy? Now, these are in the same column, okay? They're the same column. So if you need to borrow $1, who would it be easiest to steal from or borrow?
PB.
Exactly, PB, okay? So the first thing, anytime we're looking at any trend, so I'm glad you brought that up, okay? Because your reasoning was right. Anytime we're looking at trends, the first thing you should ask yourself is, are they in the same row? Are they in the same row? Or are they in the same column, okay? Because depending on that changes what factor we're looking at. So again, like say for instance on this one, okay, another thing, if we think about, let's think about arrows, for example. So remember we did that Coulombic attraction quiz the other day, okay? If we were looking at these 3, I know you guys are gonna have to think back for this. Remember they had the arrows. Remember they had one arrow that looked like this, and then they had another arrow and it looked like this, and then they had another arrow and it looked like this. Oof, okay. Which one of these guys between fluorine, chlorine, and iodine, who do you think would have had the thickest arrow, which means the strongest force of attraction between the nucleus and his electrons? Fluorine would have gotten this big, thick arrow, okay? Because look, his electrons are literally right next to his nucleus. Like, look, they're literally, I can't even get the whole thing there. They're right here. But this one, okay, iodine, look how long I have to make this arrow. Look how far his electrons are from his nucleus, okay? That's why it's so easy to steal from him. If this is a magnet and there's an attraction between these, the only electrons we can steal from an atom are the ones on the outside ring, okay? So the further away they get from the nucleus, the less likely the atom is to know that we're stealing them, okay? He's like, I mean, I got all these other electrons. These are pretty far out. It's a lot easier to steal from him than it is from fluorine, where his electrons are right next to his nucleus, okay? Well, that's a good question. I'm glad you asked that. All right, so now that let's do maybe one more for, well, let's flow from ionization energy um, into atomic radius. Or let's recap electronegativity. All right, so if you remember the other day, there was an element I told you to remember for electronegativity. I said he is the most electronegative on the whole table. Does anybody remember who that was? Nobody wanted electrons more than him. Nobody.
Fluorine.
Thank you. Yes. And Melissa, yes, exactly. Fluorine. Nobody, she told me in the chat, nobody wanted electrons more than fluorine. Okay. So remember, as long as you are moving towards fluorine, you are increasing in electronegativity. So electronegativity and ionization energy actually have the same trend. As long as I'm moving towards the guy who wants the electrons the most, I'm also moving towards the guy who would be the hardest to steal from. Same thing if I go up and down. If this guy is the hardest to steal from, he's also the one who wants them the most, okay? So the good thing about electronegativity and ionization energy is that the trend is the same. So I could also write increase up, or remember, you can also say decrease down for electronegativity as well. I do not want that. There we go. Increase up. All right, so now we've covered electronegativity and ionization energy, and you are going to get some practice with this, but I do want to recap atomic radius. Okay, so let's recap atomic radius. Atomic radius, let me just get this arrow out of the way here. Atomic radius, okay. Atomic radius just has to do with size. Okay, how big is the atom? Remember, radius is like the radius of a circle. Okay, so let's use these same ones. Okay, usually atomic radius is pretty easy to see if you're within the same family. So again, remember, the first thing you should ask yourself is, are these in the same family or are they in the same row? So if we're looking at fluorine, chlorine, and iodine, same family or same row?
Both same row.
Same row. Remember, row goes this way. So these are in the same, and if you don't remember, you can think about this. What's the name of this family, right? This family. So this is a family. So fluorine, chlorine, and iodine are in the same family. Now, when I talk about atomic radius, let me save this. So let me revamp and let's do atomic radius. Okay, atomic radius is just how big is the atom, okay? That's basically all you need to know for that. All right. I don't want to clear my whole screen because I want to use these drawings. All right, so atomic radius. Right, atomic radius. Again, this is just how big is the atom. Right. Can you look at the three that I drew on the screen and obviously tell which one is bigger?
Yes.
Yes, which one is the biggest? Iodine, right? That should be, hopefully you can see by looking at these that iodine is the biggest. Now, let me ask you this, because this is where people get confused. Does the fact that iodine has 53 protons and chlorine has 17 and fluorine have 9, do you think that is the determining factor for why iodine is bigger? Okay, what about online? Somebody online. Do you think the number of protons, iodine having more protons, do you think that is the main reason why iodine is bigger than fluorine? I can call on someone specifically. Let me see.
No.
Oh, okay. Mandy says no. Mandy, is there something you see that you would say, I think iodine is bigger than the rest of them because?
Because it has more rings, probably.
Exactly. Exactly. Okay. So when we're saying
More protons in turn means more rings, though, doesn't it? So
not necessarily, not necessarily. And I'm glad you said that because I'm going to come back to that. So someone said, if you have more protons, don't you have more rings? Not necessarily. So let's finish up with what you were saying, Mandy. So yeah, so look at this. Fluorine is right here. Okay. He has 2 rings because he is on the second row. Chlorine has 3 rings because he is on the 3rd row. Iodine has, let's see, here's I. He has 5 rings because he's on the 5th row. If you are in the same family, what's going to determine whether you're bigger or not is how many rings you got. If you got a bunch of rings, you're clearly going to be bigger than someone that has 1 or 2 rings, okay? So atomic radius, when we were talking about it earlier, it would increase. That's the easy one to see, okay? It would increase or get bigger as you go down a family. So that's the easy one to see. All right, that's the easy one to see. Now, let's address the question about within the same family. Someone said, if you get more protons, don't you also have more rings? So let's see if that is true. Let's go back down here. What is happening? There we go. All right, so I'm gonna erase this. All right, let's do some that are in the same row. So if we're all in the same row, we're gonna have the same number of rings, right? But we may have more protons. So for instance, let's do, how about, let's do sodium and aluminum and argon. Okay, sodium, aluminum, and argon. All right, sodium Na has 11 protons. All right, that's his nucleus. And then aluminum has 13 protons. That's his nucleus. And then argon has 18 protons. That's his nucleus. All right, so they all have nucleus. They all are on the 3rd row. So they all have 3 rings. 1, 2, 3. 1, 2, 3. And you may remember this from our quiz over Coulombic attraction. All right, so right now they all look like they're the same size because they all have 3 rings. Now, who is there an attraction between? What 2 particles?
Oh, electron.
Protons and electrons. There's an attraction between protons and electrons. Okay, so hopefully we all know that because we know opposites attract. Now, electrons are where? James, can you tell me where we find electrons? Where are they?
In the electron cloud.
On the electron cloud. Very nice. Electron cloud, or the rings, or the shells, whatever you want to call it. Okay. So they're out here on these brown lines. So for instance, they'll be like right here. Okay, they'll be out here in this space, not in the nucleus. All right. So if those electrons are out there on the electron cloud or on the rings, okay, and they're attracted to the nucleus, of these 3, who do you think would have the strongest attraction? So let's pretend they're magnets. Let's pretend the nucleus is a magnet. Which one is the stronger magnet? Who's the stronger magnet?
Argon.
Sodium, Aluminum or argon? Sorry, go ahead.
Argon.
Argon. Excellent, Elizabeth. Argon. This one is the stronger magnet. If you are a magnet and you are stronger, would you pull things towards you or would you push them away? You're going to pull them towards you. So if these electrons are out here on these rings, okay, and this is the stronger magnet of all of these other ones, is he going to push his rings outward or is he going to pull them inward? He's going to pull them inward, okay? So all of them are going to pull their rings inward, right? Because there's an attraction. But argon is going to pull harder than sodium because this one is the stronger magnet. And we just said that if we pull them in, then realistically, argon's rings are going to be actually a little bit tighter, okay, than the other ones. So his rings are going to be just a tiny, oops, I'll just erase this now. His rings are going to be just a little bit closer in than the other guys because he is the stronger magnet, okay? Because he is the stronger magnet, he is going to be pulling those rings in just a little bit tighter. So here's the thing that is usually kind of weird to conceptualize, but you really have to think about it, okay? As I move this way being to the right, I'm saying this way. As I move this way, atomic radius is going to decrease as I move this way, okay? Atomic radius is going to decrease when I move to the right, okay? So here's what's really important when we're talking about these, okay? The first thing to ask yourself is it in the same group or the same period? That's the first thing to ask yourself, okay? If it's in the same group or same period, then you have to think about what is more important, okay? So if we're talking about atomic radius, if they're in the same group or family, the most important thing is how many rings do you have, okay? But if you're in the same period, everybody has the same number of rings. So then the most important thing is how many protons do you have, okay? So that's the first thing you have to ask yourself. And then, so I'll just make a note, if it's and this is for atomic radius specifically, okay? So for atomic radius, if it's the same group, then you think about rings, okay? If it's the same period, then you should think about protons and think about them as a magnet, okay? So who has the stronger magnet? And remember, a stronger magnet is going to pull stuff in, which makes it smaller, okay? Which makes it smaller, okay? All right, let's do just a little bit of practice with, let's just do 1 or 2 atomic radius because we kind of struggle with this last period. Let's do 1 or 2 atomic radius, and then you guys have 3 fairly short quizzes. They're each like 7 questions, all right? There's one on atomic radius, it's like 7 questions. Then there's one on ionization energy, it's like 7 questions. And then there's one on electronegativity, and it's 7 questions. Then next week, we'll mix them all up, okay? All right, so let's do one for atomic radius. How about, these guys? So you got iron, I think that's ruthenium and osmium, okay? If I asked you to put these in order of, let's say, decreasing atomic radius. Now, let's talk about what that means. If I say decreasing atomic radius, I'm going to do some erasing. I'm gonna erase right here. All right, if I say decreasing atomic radius, decreasing, who should come first? Is it the biggest one or the smallest one? So decreasing atomic radius. That means the biggest one should come first. And then you should go to the smallest. Okay, atomic radius. So you should list these. So let's put them, throw them in the chat for me. These are your three, F, E, R, U, and O, S. I want you to list them from biggest to smallest. Throw them in the chat for me. And then, all right, so you should have had, OS should have been listed first, then RU, then FE. So now what you have 3 quizzes on Schoology. You have 2 attempts for each. And I think you have time to finish all 3. All right. I am going to erase this. I'll just clear everything. All right. Hopefully you took good notes and you can start your quizzes.